Hello and welcome again to all. Our first speaker is Rana Mutashar, but we have to wait a little bit because she had some Wi-Fi problem. So we have to wait a couple of minutes. Sorry for the delay, by the way. We will wait until 3:30 and after we will start it. Mr. Sadegh Lajevardi, I think, is here. Sir, are you available to present?
Sorry, could you pardon me? Could you tell?
Hello, can you hear me?
Yes, this is Sadegh. Hello.
Hi, Mr. Sadegh. Our first presenter is absent, right? Right now, are you available for presentation?
Yes, I am at your service.
Okay.
So I can start. Wait a minute.
Okay, I will have to. So I'm start with introduce myself. I'm Dilara Akdoganbulut. I'm moderator of this session, session 3, and session title is Digital Bridge Engineering. And now the session will start with Mr. Sadegh Lajevardi.
So, could you see my screen? Hello, everybody.
Yes.
Okay. So I would like to know if you could see my screen.
Yes,
okay.
We can see your screen. Thank you.
Very well. Okay. Hello, everybody. Good afternoon. It's an honor for me to present my paper in front of a great audience. This is Sadegh Lajevardi. This research developed under supervision of Professor Lorenzo, Professor Oliveira, and Professor Matus and Dr. Souza. So for the first step, I would like to present the motivation about my research title. The research title is Operation Reliability Index for Maintenance Decision Making in Bridges. And for maintenance management, it's necessary to optimize cost for decision making, and also for this manner, there are several tools has been applied for decision making, such as mathematical tools and other systems such as decision tree and etc. So in this research, uncertainty of defect probability combined with other items such as availability, performance, and also their overall equipment effective index to find the priority maintenance, and then it's possible for decision maker to find the reliability and decision making. To demonstrate the usage of this method and also this method capacity in analyze model, I will show the case study with combination of decision tree and also overall railway infrastructure effectiveness. So for this manner, overall railway infrastructure effectiveness will present based on the infrastructure equipment availability and also their performance rate and their infrastructure quality rate. So for finding the quality rate, it's necessary to apply the visual inspection, and also for performance and availability, the data will applied from delay and operation time and etc. So for the item A, the availability, it is necessary to find the infrastructure failure, which is the function of the allocated uptime. We will present it with UT and also unplanned downtime due to the infrastructure failure, and also unplanned downtime due to overdue maintenance activities, as you could see in this formula A. For the next parameter, it is necessary to calculate TTOT, which is represented scheduled total train operation time, TDNMR, train delay, sorry, do you have my screen or? Okay, the quality rate is a function of measured Q value, and it's a deviation from the stated quality limit. In overall equipment
Sadegh,
effectiveness.
excuse me, sorry, we cannot see your PowerPoint presentation.
Okay. Okay, I will start it again, sorry. Oh, how can I solve it? Maybe. Okay.
What kind of problem do you have right now?
I don't know, because maybe I have to join again.
Sure.
Okay, I will leave and again. Oh, okay.
Did you try share screen?
I can't find it, yes. So.
Okay, handle it. Thank you.
You're welcome.
Now we can see your presentation.
Okay, very well. So the quality rate is a function, sorry. The quality rate is a function of measured Q value, as I told you, and also for the overall equipment index, it will be between 0 to 100, but if we suppose the quality limit less than quality value, it's possible to exceed than 1, and also quality value can have a higher value than a stated Q limit if track section, railway track section and bridge standard is higher than the stated objectives. Okay, and also this research case study was located in Tehran subway in a main line, and the operation time start 5:30 in the morning till 2:23 at the night. And based on the operation time, the allocated uptime has been calculated, and some other items such as delay and operation time, suppose in the real case, based on the next slide table, you could see here proposed item and also the quantity which has been supposed in our research, delay for defected equipment, delay for unserviceable status. These are calculated and considered for a definite period of time in our research, and you could see the time between each train with item head, 4 minutes between every train, the average time between the train, and also the number of car in each train, and etc. And the period of time considered for this research analyzed based on event during the time period. Also, during a month, there is a delay for maintenance due to unexpected infrastructure failure for half an hour, which has been considered as DTF, and the maintenance activity has been done between 10 a.m. to 10:30 a.m. During the definite time that I told you, we analyze our research, and for a month, TTOT has been supposed 2 hours more than UT, because in around the clock we have some operation more than planned, more than a scheduled plan for train, because maybe we need to move something between the network, and also it's more than passenger trips. So delay due to speed reduction was considered 6 hours in that month, because we have some emergency maintenance, and based on the record events, it has been done during the night when the service operation has been stopped. And also, as you could see in this slide, the first result for the first step of our decision making in maintenance, beam, drainage, and abutment are the highest value in this case based on quality state and the cost for repairing. And in this case, we have to focus on beam, drainage, and abutment to compare other equipment in our bridge. For the second result, the overall railway infrastructure effectiveness value has been illustrated in this slide, which considered the delay for availability, quality, and the member performance. And the item will help decision makers for finding the degradation model and finding the bridge priority to compare other bridges in that road and in that network. For example, for this bridge, the total overall railway infrastructure equipment effectiveness is a 91%, And if some other, for example, railway bridge in that network is lower or higher, we can decide about their priority to maintenance. For the final decision-making step, rely on maintenance method. As you could see in this slide, there are 4 level or 4 type of maintenance method considered in this research: run to fail without any interval inspection and any preventive maintenance, which is represented the poorest level of maintenance, and also the unserviceable level, which is representing the lowest level of preventive maintenance, with emergency maintenance and several operation disorder and delay. And you could see defected level, which is lead to several defects with some seldom operation disorders, and the perfect level, which is prepare higher quality based on combination of condition monitoring for sensitive equipment and interval inspection for important and risky equipment. As you could see in that decision tree diagram, run to fail has a big investment for decision making and maintenance, and also for preventive maintenance. You could see the 3 level, and the best one for optimized maintenance is defected level, as you could see. And also, okay. For the conclusion, we have 3 steps in maintenance decision making. In the first step, it's necessary to clustering the bridges and their component level of quality to decide about their priority and their equipment with regard to their cost repair. And you could see the importance equipment in this slide. So for the second step, for operation management, technical aspect and quality level is not adequate for decision making about their priority level of maintenance for bridge in the network. Therefore, for the final step, it's necessary to find the overall railway effectiveness index, and it's possible to trend the state of this index during the operation over the time and predict the future status. In this case, this index has been calculated 91% or 0.9. Sorry. Thank you for your attention. I hope this presentation is helpful for maintenance decision makers. Thank you so much.
I'm sorry, some problems occurred. Sorry for the communication problems.
Okay.
Thank you,
You're welcome.
Mr. Sadegh.
Thank you.
Do you have any question for Mr. Sadegh? I think there's no question.
Thank you so
Thank
much.
you. Thank you. Now we will continue with Rana Mutashar. Dear Rana Mutashar, can you hear me?
Yes, I can hear you.
Okay. If you are able to presentation, we can start with you.
How can I show my, do you know?
For sharing your screen, bottom part menu, you will see the share screen part button. I'm sorry. I think now we can see your.
They said you cannot start screen share.
I'm sorry, I couldn't hear you.
It said you cannot start screen share.
Okay. Let me check just a second.
Okay.
I checked our settings and share screen now able to for you.
Yes.
Can you please try one more time?
Yes, I do. Is now okay?
Yes, perfect. Thank you.
Yeah. Good afternoon, everyone. My name is Rana Mutashar. I am PhD from Ohio University. I'm working now in Territon Corporation in West Virginia, Boca. I will present today my research with the title is Shear Correction Live Load Distribution Factor for Skewed Composite Adjacent Box Beam Bridge. This presentation will contain first introduction. I will talk about the adjacent box beam bridge, and then I will talk about the correction for shear for a live load distribution factor based on the LRFD 2017. Then I will talk about the objective of this study, methodology, result, and conclusion. Introduction. Adjacent box beam bridge is more popular used in the United States. That's because of their advantage in terms of easy of construction, the economy, and the high span to depth. This is the figure below. It's showing that more of the state in the United States use this type of the bridge in design of the bridge with the short and the medium span. The adjacent box beam bridge is constructed by multi-beam placed side by side. These beams are transversely connected using full depth and partial depth shear key and the transverse tie rod. The shear key is grouted with non-shrinkage or UHPC grout material. The adjacent box beam bridge is constructed either straight or with the skew angle. However, many states have some restriction about the maximum bridge skew angle. It is like most of the state, 80% of the state use the 45 as the maximum skew angle. However, other state is building this bridge with the 60 skew angle. The adjacent box beam bridge is constructed either with the 2-inch asphalt overlay and called non-composite adjacent box beam, or it is constructed with the 6 to 8 inches reinforcement concrete deck, and this one is called composite adjacent box beam. For this bridge and under research, it is skewed. We will focus in a skewed composite adjacent box beam bridge. For Ashto, LRFD 2017 is presented to the correction factor for the moment and the shear. For the moment, it's showing that with the increase the skew angle, the moment in the longitudinal direction is reduced. For the shear, it's showing that the distribution factor is increased with the increasing the skew angle. This figure below show how the distribution factor increase with the skew is reached to 1.6 when the skew angle equal to 60 degrees. But the adjacent for the Ashto did not present, like it say the correction, it will be at the obtuse corner and conservatively will be used for hold the beam, but it did not discuss like how the shear will be like vary along the exterior girder, along the interior girder, how it is be for the exterior and the interior. The objective of this study is to quantify the live load correction factor for skew composite adjacent box beam, and then investigation how the correction of the shear is vary along the exterior beam and how the shear correction is vary along the bearing line. Bridge description. For a bridge under study, it's a bridge located in Ohio, Leung County in United States. This bridge has a 90-foot long, and it is with the integral abutment and have the 28 skew angle. The bridge is designed for an HL93 live load. This is the framing plan for the bridge. The bridge consists of the 7 beams. It's placed side by side. These beams are connection will have with the half shear, partial shear key, and with the transverse tie rod. Based on the Ohio Department of Transportation restriction for the adjacent box beam bridge with the 28 skew angle, each 2 beams were connected using 1 tie rod, like staggered normal to the beam axis. This is the cross section of the beam. The beam have the depth 33 inches and width is 42 inches. The end of the beam is sitting on the 3 bearing pad is placed parallel to the abutment, and the longitudinal reinforcement from the beams it is like extension to abutment. That is to make the integral abutment. The cross section of the bridge is showing in this figure. The beams are placed like I said before, side by side, and there is 6 inches reinforcement concrete reinforced with the number 6 reinforcement bar at 18 inches center to center. Field test. This field test was used to just validate the finite element, because the modeling of adjacent composite adjacent box beam bridge with the all component is have some complexity. Increase this complexity by the skew angle, so we need to verify the finite element before we can use it for study the correction of the shear. So for the field test, this is the plan of the instrumentation. The bridge was instrumented with the strain gauge and the LVDT, the strain gauge to measure the strain and the LVDT to measure the deflection. This is the cross section. It's showing where we put the instrumentation plan. We put like the strain gauge under each beam at the mid span of the beam, and for each joint there are 2 LVDT to measure how much the deflection and the relative deflection between the beams. This is showing the frame that we built before the day of the testing to support the LVDT. If you see the picture, there is a frame, and then in a small picture, it's showing where the LVDT is. And this is in the day of the testing, we use 2 tracks, single axle track and dump track. The single axle track and both of these tracks were like the weight was taken in the day of the testing. And we use 4 cases of the testing. The first one, we put the dump truck on the lane 1 and single axle truck on the lane 2. In the load case 2, we switch it. We put the single axle in the lane 1 and the dump truck in the lane 2. In the load case 3, it is a dump truck on the lane 1, and the load case 4 is the dump truck on lane 4. The finite element analysis. The finite element analysis is consists of modeling a deck using the 8-node block element and modeling of the box beam, shear key, tie rod, and a longitudinal reinforcement. The longitudinal reinforcement is including the pre-stress and the reinforcement in the deck. For the analysis, we use it Abacus because it's provided us for doing linear and non-linear analysis, and also provided some flexibility for modeling different parts and the connection. For the connection between the deck and the beam, it is assumed full connection. So it's like it's working as a composite section. For material properties, this is the table showing the material properties, which is including compressive strength, tensile strength, modulus of elasticity, and the Poisson's ratio. For compressive strength, these values was measured in the lab. We take some samples during the bridge construction and transfer to the lab to measure the compressive strength and to measure the tensile strength. And using the LRFD for calculate the modulus of elasticity. This is the finite element when using the load from different of the from the research and the experiment. I found that the loading the bridge with the 2 adjacent lane load to track with the 2 adjacent lane load, it will be make a maximum it will maximize the shear. And to find the location of the load through the bridge, the load was transferred along the length of the bridge and in the transverse direction, both to maximize the shear in exterior when we study the exterior, and interior when started to study the interior beam. This is the finite element. We did the modeling for the skew angle 0, I mean non-skew bridge. I did also modeling for the bridge with the 28 skew angle and the bridge with the 48 skew angle. الأجدى LRFD shear correction factor. الأجدى provided two cases for the adjacent box beam, case F and case G. Case F is related to the adjacent box beam bridge that constructed without the transverse die rod, which is like in this case it's the bridge under study adjacent box beam with the concrete overlay. In the case G, they like it's dealing with a bridge with or without the transfer post tension, which is also applied for the bridge under study because the bridge have the tie rod. This is the correction for the live load distribution factor showing in the LRFD 2017, which is related to the length of the bridge and the depth of the beam and the skew angle. A result. First, we did the finite element analysis and validation of the finite element. Here I will just present it for 2 cases, but we did for 4 cases. For a case when we put for loading the 2-lane load, this is the result of the finite element, and showing how they close the finite element with the experiment, which is showing how it is like the finite element agreement with the experimental. And this is showing for strain and the deflection. Here it is for 1-lane load. From that, we feeling like the finite element model it's good to study the effect of the shear. The evaluation of the secu on shear along the exterior beam, and we did like evaluation for the shear along the exterior beam and along the bearing line. For exterior beam, we did for each a 10th point, and we compare it with the non-secu bridge, like with the right bridge, due to normalization and the correction for the 10th, then normalize it for the correction at the obtuse corner, which I mean, like we did the calculation of how much the shear along the exterior beam for the secu bridge. Like if we go to the other support at the obtuse corner, this is much of the shear. For example, we said 25, it's 25 kip is the shear at the obtuse corner for the bridge with the secu angle. And then this value, compare it with the value with at the same location for identical bridge when it is non-secu. For example, if we say like for this one, say 20. So we divided 25 by 20, we got how much the normalized, how much the correction factor for the shear. And then for all like along the beam, we normalized these shear values with the one at the obtuse corner. So this is the figure show how much the shear correction along the exterior beam for the bridge with the secu angle 28 and 45. And as said that before, like we use the maximum 45 degree because most of the state in United States, like 80%, use it the 45 as the maximum secu angle. From that figure, we can see like the correction factor at the obtuse corner is 1, and then it is reduced with the length of the beam, and to become 0, like for 28 degree, it's become 0, which means 0. It means like the shear for the secu angle at this point is equal the shear for the beam with the straight angle. I mean non-secu beam at the point 4, and then it is coming down to minus. Minus, it means the shear at the acute corner is less than the shear for the straight or for non-secu bridge. So at the obtuse corner, the shear for the secu bridge is more than the shear for non-secu bridge. At the acute corner, the shear of the secu bridge is less than the shear for the non-secu bridge. And the same we can see like the behavior for 28 degree, it's look like the same as 45 degree. There is some exception, like if we look here for the 48, it's become 0 at 0.5, while the acute corner is less, which means it's with the increase the secu angle, the load at the acute corner is become less, comparing with the bridge with non-secu bridge. This is the figure show how the shear would vary along the bearing line. We can see like for this is like girder 1, 2, 3, 4, 5. It's the number of the girders. Like this number 1 is the girder 1 at the obtuse corner, and then it is coming back to the acute corner. We can see like at the obtuse corner, the normalization, it's 1. And at the acute corner is coming to minus, which is indicate again that the shear at the acute corner is less than for the secu bridge than and non-secu bridge. But again, the behavior, it's showing like it's come of the similar, and I think it is need to have more research about that. and do some recommendation of how the shear is changing along the bearing line, because the LRD, it's using that the shear, it is equal for all the bridge and applied conservatively, but we need to do this variation. This is just like part of the big research we're doing here in the United States for understanding how the shear is changing along the bridge for interior and the exterior girder. So for the first conclusion is like from the result, we saw like the variation of the secure correction factor for an end shear with the H beam across the bearing line is not significantly changed. I mean, it's not significantly in a behavior, not in a magnitude. The magnitude is changed, but behavior with the secure angle. The end shear of the exterior girder at the obtuse corner of a bridge varies along the bearing line to be a negative at the acute corner, and the variation of a secure correction factor for shear along the length of an exterior beam of the span. The variation is the correction factor is significant influence by change of the secure. The correction factor variation for shear along the length of an exterior girder vary from this initial at the obtuse corner to the negative magnitude at the acute corner. Thank you.
Thank you.
If anyone have any question.
I think there is no question. Okay, thank you, Ms. Rana Mutashar, for informative presentation. Thank you.
Thank you.
Okay, now we will continue with Captain Tam's presentation. Captain Tam, are you ready for presentation?
Yes, I am. Sorry, I wasn't able to change my screen name. My name is Kwok Leung Tam. So I'm ready. Let me try to share my screen. Let me know if you see my screen.
Yes, we can see.
Okay. Thank you. My name is Kwok Leung Tam. I work for WSP New York office. Now it's 8:10 a.m. from New York. So good morning, everyone from New York. So let's get into today's presentation. So the picture shown on the screen is the complete main span structure of the east span and the west span bridge. And this presentation is for the replacement of the Kosciuszko Bridge Phase 2 project. And this project is to replace the 77-year-old old bridge. And the project was complete 4 years ahead of schedule and was the first new major bridge crossing complete in New York City since the opening of the Zordan Bridge in 1964. Today's agendas: project introduction, project history, west span main bridge design and construction, existing bridge demolitions. Then we have question and answers. Project locations. The new bridge is located in New York City, and the bridge system is part of the Brooklyn-Queens Expressway in New York City. It's connecting from Greenpoint, Brooklyn to Mansfield in Queens, which carry the Interstate 278 and crossing the Newtown Creek. The project is divided into three segments. The main span segments, Brooklyn-Queens approach segments and Brooklyn-Queens connected segments. And the project also divided into 2 phases, where you see my laser point. This is the phase 1 project. It's a design build project, and the phase 2 is design build project. And phase 1 was constructed by SKE and designed by HNTB. WSP assists New York State DOT to manage the project and provide QA and QC review. And phase 2 was constructed by Granite Construction. The connected segments was designed by Harris and Hanover. The approach segment, including the Brooklyn and Queens approach, and the main span were designed by WSP. I was responsible for the independent check on the eastbound main bridge, and on the westbound, I was responsible for the design and joint construction. I provide QA, QC review, and I was also a site engineer, joined the westbound design, and I was on site coordinating the construction with the contractor and also the New York State DOT persons. And existing structures. The existing structure is a steel truss, two-truss bridge. It's built in 1939. It's named Meager Avenue Bridge. After 77 years of service of the existing bridge, the structural steel, the concrete roadway is heavily deteriorated, and traffic is heavy throughout the day. By year 2015, the bridge system is carrying 19 times the amount of traffic compared to its original design for. In 2009, New York State DOT decides to replace the bridge system. On the screen are the construction sequence for phase 1 and phase 2. For phase 1, to start to build a new eastbound bridge next to the existing bridge, then shift all existing 6-lane traffic from existing bridge to the new eastbound bridge, then remove the existing bridge. Then phase 2 is to build a new westbound bridge next to the eastbound bridge, then shift the westbound traffic from the eastbound to the westbound roadway, and also open a pedestrian walkway too. And during the main span design phase, 4 types of main span were studied: box girder, dead arch, dual arch, and cable stay bridge. And the cable stay bridge option was selected by New York State DOT. And on the screen is the rendering of the phase 1 and phase 2 construction. We start with existing bridge. Construct a new eastbound bridge next to the existing bridge. Remove the existing bridge. Then construct a new westbound bridge next to the new eastbound bridge. Phase 1 eastbound bridge, again, is a design build project. The contract value is $555 million. It's under the Governor New York Work Program. It's designed by HNTB, constructed by SKE. WSP provide design, QA, and oversight to this project. And the bridge system was open traffic on April 2017. And phase 2 westbound bridge, designed by WSP, constructed by Granite Construction. The contract value is $318 million, and the bridge system was open traffic on August 31st, 2019. Phase 1 and phase 2 on the screen shows the elevation view of the eastbound and the westbound bridge, and they are independent bridge system. And if you overlay them, look from far away to the bridge system, right, you will see the bottom image when you look far away. And main span foundation layout, we had the pylon WB10, and you can see from this key view, and the power cap are supported by dual shaft. And we have 2 anchor piers, WB9 and WB11, and you can see from this key view. And the the power caps are supported by driven piles. The pylon, about 277 feet high, is an independent pylon. The pylon height is restricted due to FAA restriction and also span to height ratio. And it's an independent pylon because it doesn't have a cross beam to tie the two vertical columns together. And you also can see it from this photo. There is no cross beam. And what you see on the screen is the superstructure, which is sitting on the edge of the column. We have three typical pylon section. Section A is the upper pylon, which contain the steel anchor bars. Section B is the hollow sections. Section C is the lower pylon. It's designed as a hollow section, but it's also designed to fill with not structural concrete to reduce future maintenance costs. The pylon foundations, the power caps are 35 by 35 and 12 feet high, and each power cap is supported by 7 feet diameter drill shaft. And this is the typical drill shaft sections. And the drill shaft go into ground 180 feet deep. And also at the end of the drill shaft, we also have a 6 feet watt socket. The length of the watt socket is about 13 feet long. And at the upper pylon, we have the steel anchor bars for the upper cable to anchor to the pylon, and the steel anchor bars consists of 4 welded steel plate, and 3 sides of the welded steel plate is welded with shear stud, and these 3 sides of the plate are poured with the pylon concrete to make composite with the pylon concrete. So the cable load will transfer to the steel anchor bars, then distributed to the concrete. And on this side of the anchor bars, we have an opening, and inspectors and maintenance crew can access the inside of anchor bars using the interior ladder and platforms. And on this isometric view, you can see the open side of the steel bars. And this is the elevation view of the steel anchor bars system. And 3 levels of anchor bars make up 1 segment. And this is the where the cable is. And this picture shows the welded shear stud side of the steel anchor bars. And this picture shows the open sides of the steel anchor bars. And we have 2 anchor pairs, and each one is at the end of the main span away from the pylon. And the cap beam is 10 by 12 feet and is supported by 2 7 feet diameter column. And the power caps are supported by 18-inch diameter concrete filter pipe pile. And we also have a ladle with stringer block cast in place on top of the cap beam to provide a guide for the superstructure to move longitudinally. And this view shows the pile detail in a elevation view, and this is a picture of the pipe piles. And this is the main span superstructure framing plan. We have 2 edge girder. You can see it, my laser point, and they are both run continuously between the pylons. But to accommodate the pylon geometry and the cable geometry, there's a cane at the edge girder to avoid the pylon column leg. And we have 12 different type of forebeams. At the main span, the forebeam spacing is about 13.5 feet, and the back span is 14 feet. The counterweight region, the forebeam spacings are 7 feet to 9 feet to accommodate the heavier counterweight. And the cable anchors are outboard from the edge girder. We have 2 cable planks, and each cable plank we have 28 cables, 14 on the main span side and 14 on the back span side. And that plan, at the end of the bed span, there is a little horizontal curve. To accommodate this horizontal curve, the deck is poured to accommodate the curve, but the steel framing is designed and built square. This is the superstructure. We have two edge girders. The forebeam is bolted from edge girder to edge girders, and the cable anchors are outboard from the edge girders. The precast panel is supported by the forebeam and the edge girders, and we also have a infill concrete to make composite of the precast panel with the forebeam and the edge girders. The weld spine is designed for 4-lane traffic, and we have a 20 feet wide roadway walkway. The entire deck is about 93 feet wide. And the superstructure cable anchor, again, they are outboard from the edge girder. You can see from this view, the cable anchor consists of welded steel plate and steel pipe, and the assembly are put together. Then they are bolted to the web top flange and bottom flange of the edge girder. And more view on the cable pipe. And this is a construction photo of the cable assembly, anchor assembly that is bolted to the edge girder. And this is a erected segments. And to accommodate the deck tension in the deck near the anchor pier WB9 and WB11, we designed and installed 65 longitudinal post-tensioning inside of the deck. And this is the location of the longitudinal tendons. This is the WB9 pier, and this is the WB11 piers. And this is the cross section of the typical section of the concrete deck. And where you see the red circles are location of the PT duct. And this is the PT duct post-tensioning system that we use in the project. And each tendon consists of 4 cable strands, and they are anchored to an anchor bearing plate and with a wedge, and a plastic cap is used to protect the system. And the main span stay cables. The cables are anchored from the deck level to the pylon anchor bars. The pylon is using the fixed anchor, and at the deck level we use a adjustable anchor. The cable strands are 0.62 inch diameter uncoiled, 7 wire strands, and they meet the requirement of the ASTM A416. Each strands are waxed and sheeted, and they are erected inside of a HDPE pipe. And the system is designed to erect, install, and replace the strands one at a time. And we also have an internal damper installed, and you can see the internal damper is clamped to the strands. And you can see this is a picture of the damper that is installed. Once the cable is stretched to the required length, the strands are cut to the required length, and a cap will be installed, and a liquid wax will be injected into the voided area to protect the cables. And due to the unbalanced length between the main span and the bed span, we have a counterweight designed and constructed at the end of the side span. And this is a section view of the counterweight, and this section is cut between the edge girders. And you can see this is the location of the forebeams. And we have 5 typical counterweight bay, and the construction sequence in this bolt-up view is install the precast panel first, pour the leveling slab, then install the steel ingot on top of the leveling slab, then pour the encasement concrete, then install the precast panel, and pour the infill concrete to make the deck composite with the steel framing. And excuse me, this too is a in-climate bay. This counterweight bay only have concrete only, it doesn't have steel ingot. And this construction photo showing the steel ingot is installed, and they are in the process of pouring the infill concrete. And under the main span we also design and install a maintenance inspection traveler, and the traveler is allowed to travel between anchor pairs to anchor pair, and you can see from this key wheel. And the traveler is supported by two traveling wheel. The traveling wheel are bolted to the bottom of the forebeams, and we have two extension platform that can extend it from the end of the traveler and extend it beyond the cable anchor and the forebeam to provide access to the cable anchor and also the edge girder. And this is the man lift that have been installed. And we also install a scissor lift man lift, and the man lift is to provide access to the bottom of the deck between the forebeams, and this is the scissor lift that have been installed. And to design the main span is a complex process to capture the actual behavior of the cable stay bridge. We create a 3D model in Mitre Civil, and we use Mitre Civil to analyze dead load, live load, wind load, temperature load, depth post tensioning, and seismic from response spectrum analysis and time history analysis. And all this loading are combined according to the ASTRO LFD load combinations. And you can see this view of the model, and the cap beam, the columns, and the forebeam edge girders, and the spine of the approach is modeled with linear elastic beams, and the cable are modeled with truss members, and the foundation are simulated by 6x6 matrix. And on the screen shows the result of the frequency analysis from the Midas model. Mode 1 is the vertical mode, mode 6 is the main span torsional mode. And this movie captures the result of the time history analysis. The motion on the movie is correspond to the force function applied to the substructure. You can see on the bottom left of the screen the time function that applied to it. The movie, the motion on the movie is exaggerated. And due to the main span bridge type, aerodynamic effect is an important part of the bridge design. And we have two type of model that were created for the wind tunnel test. And it was the test was conducted by RWDI, our sub-consultant, and also the model is also created by RWDI. The first model is the sectional model, and you can see from this view, and the model is constructed with plywood, aluminum strip, and plastic part that are printed from a 3D printers. And the model geometric shape and the structural dynamic property of the model is scaled down to match with the actual bridge system, and is scaled 1 to 60. At the end of the model is attached to a spring system. The spring system is to provide frequency adjustment to the model, and also used to collect data for the test. And you can see from this picture that looking up from bottom of the deck, and this is the wheel showing the cable anchor. And also the model is allowed to rotate in a different angle to simulate a different wind attack to the model. The second model that have been created is the aero-elastic model, and the material that used to create this model is similar to the sectional model test, and the cable is modeled with piano wire. And at each end of the main span, 400 feet long of the approach span is modeled and attached to the main bridge model to provide boundary conditions to the main span test. The model is also amount to a turntable, and the turntable is allowed to turn in a different angle to simulate a different angle of wind attack to the main bridge model. Besides the Midas model, we also have a 2D model called is model in Tango. We use this model to do a independent check for dead load, live load, for construction stage analysis, cable loss, and cable replacement. And this movie shows the construction stage of the main span is constructed with balanced cantilever method. Tango is a 4-chan program. It doesn't have a high definition graphic, but this movie should be able to give everyone an overall view how the main span was constructed. And this is a picture of one of the erection construction photos, and you can see from this picture at this end, the contractor erect the forebeam and the edge girder already, and his next step will be installing the cable and installing precast panels. And on this side, you can see that there is a temporary support at the back span, and this temporary support is required to install and have it at this construction stage to stabilize the overall structures. And the existing bridge demolitions, and the movie is showing how the existing bridge is taken down, and that was done for the approach span. And it's amazing that we can do this in New York City. And the photo on the left side is the main span bridge. It was cut down and shipped out to avoid impact to the Newtown Creek. And this is my the end of my presentations. Thank you.
Thank you, Mr. Kwok Leung Tam, for informative presentation.
Thank you.
Up to now, do you have any question for Mr. Tam? I think there is no question.
Thank you.
Thank you again for your presentation. Mr. Tam, could you please
Yes, I am
sharing?
trying to stop sharing.
Okay. Okay, now we will continue with Mr. Tobia Zordan's presentation. Mr. Zordan, can you hear us?
I'm
Hello.
online. Hello. I will share my screen. Do you see it?
Yes.
Okay. So thank you for this invitation. I'm very proud to be here with you. Thank you to the organizers and thank you to the audience for joining this presentation. The topic will be a bridge fast condition rating systems. I will introduce very quickly the topic, make a few considerations, very general considerations, and then I will talk about an application, a BMS that was recently developed by my company together with an IT company. I'm sure you know this bridge. This bridge is Morandi Bridge. 2 years ago it collapsed, and this is a picture with a slide with some pictures from the opening in 1967. And this bridge and all the event that followed the collapse of Morandi Bridge concerning Italy are the main reasons for a very big urge in the use of these systems from our government, and a very fast and big development of all the systems that I mentioned. You have to consider that this bridge, Morandi Bridge, as well as other bridges, were built in between the 50s and the 60s in Italy, where we had the so-called post-World War economic miracle. So the large majority of the Italian bridges now are exceeding the lifespan. And we are facing big problems in maintaining and keeping those bridges fit. Morandi Bridge, somehow, it is considered as a peak of an iceberg, because we are now realizing that we have, in general, a lot of problems in maintaining our assets in a good condition. And we are facing, nowadays, we are facing very big risks with the need of acknowledge a wide awareness about the state of conservation of our asset. This bridge collapsed in August 14, 2018. It has been discussed and presented in many occasions, many symposia, many conferences. So I won't lose any time in talking about this bridge. The bridge was demolished with a controlled demolition, and a new bridge was inaugurated on August 3rd, 2020. Just let me share one idea with you, because I will get back to this idea later in this presentation. Morandi Bridge was extensively monitored. So this bridge was, let's say, under control, or should have been considered a bridge under control. Nevertheless, very suddenly it collapsed. So this fact, I mean, the very sudden and unexpected collapse, together with the fact that a lot of instrumentation was installed on the bridge and data were gathered, made a real shock to the Italian public opinion, and really was a benchmark. We got to a crossroad, and everything changed after the collapse of this bridge. Morandi Bridge, as I told you, was the peak of the iceberg, because after and before the collapse of Morandi Bridge, we experienced several other collapses for different reasons. Now, of course, there are a lot of statistics, there are a lot of presentations, and there is a wide awareness about the state of our infrastructures. And we know now that almost all our territory is in danger, and we are dealing with a map which is showing a map of risk, which is showing a very spread risk all over the country. There are data, of course. Italy is not the only European country facing this problem. We have statistics showing, for instance, for railway bridges, which is the age profile of the European bridges. And if we consider bridges which are over 50 years old, we see that a very large majority, and pretty much more than 50% of our asset, European asset, considering railway bridges, is exceeding the lifespan, the design lifespan. But also not for railway bridges, also for road bridges. Europe is displaying a situation which is somehow critical. You see here for different European countries, and again, if we consider bridges that are over 20 years, we see that pretty much a large majority of these bridges is again exceeding or is quite next to start to exceed the lifespan. What about the United States? It seems that in the United States, the situation might be considered a little bit better, but these data are not fully recent. Maybe they are not fully updated, but we can see that these data are from the Federal Highway Administration, that quite a lot of bridges are exceeding the lifespan, and also for the bridges which are not exceeding lifespan, we can see that the total number of structurally deficient bridges or obsolete bridges is not negligible. So we are starting to understand that this is a very common problem. And what are the most affected bridges by this problem? Well, again, if we go back to Europe and we consider the type of material constituting the bridges that we are analyzing, we see that this problem is largely affecting pre-stressed concrete bridges and concrete bridges, which is again the largest majority, at least in Europe, of the type of bridges that we are dealing with. And if we consider what is the span of the bridges that are impacted by this problem, we see that typically for many European countries, spans are small spans. So we are not talking about big bridges, we are talking about small conventional, small and medium span bridges, which are almost all the bridges that we have. So we are talking about a huge problem now. What is the strategy? What is the strategy of European countries? Different countries have different strategies, of course, but in general, we proceed by rehabilitating and strengthening the existing bridges. Just a few countries are facing this problem, replacing the bridges that are exceeding the lifespan and that are in need for maintenance. You see here some data from the Netherlands, but if you go to Spain, you see the approach is pretty much the same. So replacement is indicated in a small minority of existing bridges. Sweden probably is the only European country with different strategies, but Sweden is not representative. I would say is a special country with reference to this approach. Is not cannot be considered as a reference country in terms of maintenance activity and strategy for maintenance of bridges, because here you see replacement is the most common attitude. I would like to draw your attention to this plot. This plot represents the investment in European Union for the infrastructure maintenance. Different colors are here for different countries. And what is the beginning? What do we have at the beginning of this chart? We have the economical crisis, the big crisis of 2008. So I'm talking about my country. Italy reacted to the economical crisis, cutting the investment for maintenance. This is quite clear. So the investment started to recover after, then this chart is going up, this line for Italy is going up. And our country reacted by cutting very drastically the investments for the maintenance of the existing infrastructures. Here we have a list of collapses. In the last 10 years, we experienced at least 15 collapsed bridges. This can be, well, well interpreted or part interpreted, but if we consider the superimposition of these two charts, where we have in blue the line that I showed you before, with a drop of investment in Italy for the maintenance of the existing structures, and this line that is represented the number of collapsed bridges, we can identify an awkward data that is corresponding to a dramatic increase of collapses just after 4 years after this country started to disinvest in maintenance of existing structures. So we are facing a critical scenario nowadays. We are dealing with old infrastructures. We are dealing with a general lack of resources because of the economical crisis, and because the economical crisis was almost over before this new phase of pandemic started. So we are still dealing with a general lack of resources and with a general critical scenarios. And more than that, in Italy, like in other countries, we are dealing with a lack of technology and IT systems. So this, the systems for the rating or BMS or for the rating of existing assets are in general not fully implemented or are in a state of development. What is the reaction, the general reaction of the owners of an asset when facing vulnerability issues, when facing a risk? Well, in general, as you see in this chart, as vulnerability is increasing and risk is increasing, the general attitude is to introduce reliability-centered maintenance, and with this kind of maintenance, to introduce extensive monitoring systems. Structural health monitoring is certainly a beneficial action. It supplies a lot of information, but it can also be a problem. It's not usually easy to manage all the data coming from a very wide monitoring system, because the number of data collected can easily be huge, and the management and the interpretation of all these data can be a critical issue for the owner. In general, for existing bridges, the sequence of action of data and that can be helpful in order to activate a refurbishment design or a management strategies or the optimal allocation of available resources is quite long, because first of all, you need to know the bridge. So first of all, you need to understand if original data are available or not. So attainment for original documentation, maybe yes, maybe not. Geometrical survey, data transfer, investigation for defectiveness analysis, mostly in a lot of cases, experimental campaign to assess the present mechanical characteristics of materials. Implementation of finite element models that has to be calibrated upon experimental evidence, dynamic characterization and static characterization with static loading tests, finally calibration of finite element models, and finally the design, decision, strengthen, demolish, get a new bridge, keep the existing bridge. So you pass by all these steps, loading test, static loading tests, dynamic loading tests. Here we have, this bridge was designed by my company, Bolina Ingegneria, and the construction finished at the beginning of last year. That was a long design, and the owner, at the end of construction, decided to attain a dynamic characterization of the bridge in order to have a kind of identity card at the beginning of the lifespan, and use this identity card to investigate all possible changes in the structural response of the bridge. But see here, how many people, again, how many efforts are involved in this kind of process. The owner, the designer, the experimenter, and all the volunteers that are working for to create a suitable dynamic input to the bridge. So this is again a big process. We spent a couple of weeks on the bridge in order to assess the initial dynamic response and give the owner the possibility to use this data in the future for schedule control on the bridge and assessment of the future state of consistency of the bridge. All of that is a lot of work. We cannot think to extend this method to all the bridges. We cannot think to use this method to give an answer to the big need for management and assessment of large stocks. This is not suitable. This is not sustainable. It will take a lot of money. It will take too much time, at least for all these bridges that are already exceeding their lifespan. A suitable answer stays within the world of BMS, of course. BMS is dealing with a lot of different issues, but mainly is the core, or should be the core, of any kind of activities relating to the lifespan of a single bridge within a large asset. So we're starting from inspection, monitoring, structural assessment. We are introducing the deterioration or the defect models within all the inventory database. We can predict future performance. We can plan maintenance. We can optimize the allocation of economical resources, and finally take all the due decisions. There are a lot of different BMS in different countries. Today we had the opportunity already to enter into details on this topic with other presenters. I will introduce some examples of BMS tools, and I will introduce specifically a BMS that is called BridgeInit, that was developed by my company and a partner IT company in the last couple of years. Well, this is mainly the people that are involved. So we have a consulting engineering company, an IT company, partnering together in order to create this kind of tool, which is meant to be a BMS, including a fast condition rating system. What is the topic here? This tool, BridgeInit, is able to supply a rating system for a bridge in 5 working days, creating an infrastructure dossier, carrying out a risk assessment, determining the condition rating, determining the priority ranking. So where the bridge under investigation is ranking within a large list or within a large asset.
Mr. Zordan, last 9 minutes.
Yes. And finally, planning the intervention. It is working on a map, so GPS and satellite mapping, and is able to accommodate and to manage all the system of sensors that might be needed for the assessment of the structural response of the bridge. We have here two examples. One, this system is being used in Rome at the moment for the ring road of Rome, where some bridges has already been instrumented and monitored, and it's being used in Egypt in the ring road of Cairo with the same purpose. You see here some inspection activity, and you see here the main screen of the dashboard, where we have 4 levels of activity. So level 1 is basically documental, so anaglyphic, geometry, and conformity to standards. Level 2 exposure, visual inspection, vulnerability, and hazard. Level 3 is risk index, with determination of the risk for a single bridge. And finally, the output, the documentation, and the system level 4 for integrated sensor systems. The BMS is a risk-based tool evaluating the exposure of the bridge, the level of hazard, geological or seismic hazard, or other kind of possible hazards. Then there is the visual inspection for the determination of vulnerability index, basically following this flow chart, where all the elements or part of the elements of the bridge are inspected. Of course, these are the files that are staying beyond the app or beyond the what you see on your PC. So for any defect, you have checklist files. This is a file for steel piers, where you see all the defects listed, present or not present, a weight for each defect, an intensity level, and an extension level. Same thing for instance, concrete bridges. Then you have a check if the data are complete or not. You can proceed with the analysis, otherwise you have to recheck and see if the data are complete or not. And finally, you end up with a class of vulnerability for each single element and for the overall bridge. And the class of vulnerability is linking to the final determination of the risk index, which is given in terms of urgency. How urgent is the intervention on a single bridge within a big asset? There are now worked examples. I think I will give just a short highlight on the first example, because time is running out. This is the analysis of some bridges within an asset. And of course, you have this urgency index, which is ranked also for all the bridges which are in the red flag, so with an extreme urgency. In this case, the risk index within, let's say, red bridges, so with intervention, which is considered to be extremely urgent, is also given with a ranking of priority. And extremely urgent for our standard would mean within 6 months. Another example I also mentioned before, the bridge in Cairo. I will scroll very rapidly and get to the end. This bridge is a very long bridge. It is almost 4 kilometers in length, and is one bridge constituting the ring road of Cairo. Again, the condition rating, inspection here about the girders, with, I anticipated before, the extent and the intensity of any kind of defect. And the combination of extension and intensity is giving you the actual rating. The bearings, we saw there were completely burnt bearings. Other were less severe, in less conditions of severeness. Again, the bearings, the joints, longitudinal joints for 4 kilometers between the adjacent bridges, one older, one newer, and the rating. Impacts, there were several impacts with intensity and the extension again. And finally, the overall vulnerability of the bridge, considering the single vulnerability index for each single component of the bridge, and the final risk index that for the bridge in under investigation was in medium term. Medium term would mean within the next 3 to 5 years. I think the time is up. I would like to spend a lot of time with you and enter into details with all the things I've been showing to you, but I guess this is the end of my time, and therefore this is the end of the presentation. Thank you for your attention.
Thank you, Mr. Zordan, for informative presentation. Up to now, any question for Mr. Zordan's presentation? I think there is no question. Okay, thank you again, Mr. Zordan.
Thank you.
Now we will continue with Jan Osterz. Mr. Osterz, can you hear me?
Yes, I can hear you.
Hello.
Hello.
It is your turn. Present.
Yes. Okay. So let me know if you can see it.
Yes, we can see.
Okay, so if you can hear me and if you can see me, then I will begin. So, okay. So thank you for this opportunity to present this presentation here. So today I'm going to talk about pushing BIM beyond, just a second. Okay. So today I'm going to talk about pushing BIM beyond geometrical bridge modeling to a holistic digital planning platform. So many of you may not know me. My name is Jan Osterz. I'm a civil engineer and I'm also a product specialist at Alpine Infrastructure based in Graz. So to go quickly through the agenda, what I'm going to talk about today. So first of all, I would like to a bit explain what is the current state in BIM for bridges. What is happening at the moment, where we see the problems at this point. The second one, what is the vision of this holistic process, of this wholesome process where we can have one digital model for all design phases or all life cycle phases of a bridge. The next, I will present the integral software approach that we have designed, where we go from, let's say, from some general modeling to detailed modeling to analysis. And especially, I would like to focus on some of the new additions for traffic load and earthquake calculations included in this BIM process. So to first begin, what is the current state in BIM for bridges? So we can say that in the past 2 decades, there have been various attempts try to introduce BIM technology in infrastructure planning and construction projects. However, using techniques originally developed for buildings design did not prove very successful. So BIM is generally conceived as an overall strategy for coordinating all required works arising during design, construction, and operating phases of structural objects. This goal is achieved by using an integrated digital model of the structure and procedures directly communicating with it in all task settings throughout planning, construction, and lifetime. The aim is to essentially ease and accelerate the processing by avoiding errors due to multiple and redundant data entry, as well as to improve the overall quality. The effectivity of the BIM process is very much dependent on its consistent application in different use cases throughout the design and construction time and later. However, this vision of the BIM process becoming a fully integrated procedure throughout lifetime is currently not yet state-of-the-art. This applies especially to the infrastructure industry, such as bridge design, where BIM application is lagging the building construction industry. So, as mentioned, so many problems come from, for example, from entering information multiple times. Of course, we understand that the initial design needs to be communicated. Ideally, the engineer would just receive a model to work with and bases his or her work off of that. Sometimes not even that happens, and the initial design is being transferred via 2D plans, and the engineer needs to rebuild the model. That is the first stage where you can introduce inaccuracies to the design. But what if the designer, for example, changes something after the initial handover? Again, ideally, some tools check what was changed, notifies the other involved parties, and everybody can act accordingly. The second challenge is posed by increased complexity of requirements. Some things can be checked pretty in a simple manner, either manually or automatically. But once it comes to some complex requirements, 2D planning and checking can reach its limits. So the AEC, or architecture, engineering, and construction sector, has many different facets. On the one hand, you need to be able to work in a digital environment, but you also have to get your hands dirty on site. And to fill this gap and find skilled people who are capable and willing to do both is a big challenge. The last challenge I would like to name is that many complex tools are already available in the market, but the problem is there that not all of them communicate with each other. So to explain a bit what is our vision of a holistic process, here we see on the right side, we see basically how we imagine how it should be. We should have one common information model, which includes information from design, analysis, construction, and 4, 5D, and 6D information. So the optimal bridge design workflow would require digital models, which are available throughout all the phases starting from feasibility studies. They need to allow us to work faster, so we have to be in compliance with deadlines with quick and clear coordination processes. They have to offer better quality, so we have to increase the planning quality. And of course, we have to have early detection of errors and avoid multiple entries of redundant data. Of course, they also need to be more cost effective. So we need to have better cost evaluation and comparison of models. And this problem that I've mentioned before is that it needs to be open BIM. So it needs to be a standardized database. We need to have compatibility and interoperability between software solutions. So to explain a bit about this tailor-made solution for bridge engineers. So therefore, Alban Infrastructure started a few years ago with this tailor-made BIM solution for the special needs of bridge engineering, covering the full range of tasks arising in the bridge planning process, from creating a single parametric 4D model for modeling, structure analysis, design, and detailing. The heart of this solution is the bridge modeler. It is based on a strictly parametric description of the bridge geometry with an intelligent model database. It contains design parameters and development rules rather than just detailed geometric data in form of coordinates in space. This strategy allows for continuously raising the level of detail from very first conceptual design to the finally implemented structure. Continuous refinement of the geometric data allows performing visualization, checking tasks throughout the planning process, from rough cost estimates in the conceptual phase to detailed bills of materials in the construction phase. And this parametric modeling doesn't just include, let's say, the main girder of the bridge, only the body. It includes parametric tendon modeling. It has an intelligent model database. Modifications are applied to all objects of the model. And of course, it also performs visualization of the model. So once we create from this heart of the solution, what's from this geometrical model, we can use this data to create a mathematical model to allow structural analysis in accordance with accepted calculation method, and is easily derived at any point. For example, a suitable computation model in accordance with beam or finite element theory is automatically generated from the architectural model. This calculation model is then automatically updated whenever changes in the architectural model are made. A structural analysis can be performed at any stage in the process, for example, a rough analysis in the preliminary design phase with approximate model data and assuming cast-in-one construction, for example, and a detailed analysis when the detailed bridge geometry has been developed and the erection sequence has been fixed. So the first thing that I would like a bit more to focus on, which is one of the newest implementations in this solution, is the traffic load or life load evaluation. Traffic load calculation in accordance with modern design code regulations like Eurocode is a complicated process. The respective functionality has recently been released and is based on the evaluation of lane-related influence lines. Notional lanes along the bridge surface are defined in the bridge model in addition to the actual geometry data of the structure. Several constraints must be considered with respect to the arrangement of these lanes on the bridge. So different possible lane sets must be defined and different lanes must be loaded with different traffic load intensities. For getting the worst influence of traffic loading on a certain lane, load patterns, also called load trains, are required by the design code and are automatically placed along the lane in the relevant position. The extreme values resulting from different load trains and on different lanes of a lane set are superimposed. Combining this result of different possible lane sets gives the final traffic load envelope containing the relevant extreme values. And what is very important is that it's also very easy to set up these lanes, so it is very interactively. So the whole definition happens interactively in 3D, and there are two approaches how you can define this. So there is the manual definition that offers a generic approach, a code-independent approach, so it can be applied to all codes existing, or it can make use of the automatic definition that is code-dependent. At this time, the Eurocode standard is implemented, so you just select the road weight width and the auto subdivision happens, number of lanes and lane widths are automatically defined. The same goes for the definition of load trains. So there is this general approach that is also code independent with an arbitrary train position. Area line loads can be defined with a fixed length, variable length, with and without limits. Distance between loads can be defined with a fixed length and a variable length. And also including the standard Eurocode at this point, predefined trains are also inside. So the special solution for centrifugal force is also implemented with recognition of force direction and automatic calculation of force intensity. So the implemented calculation is based on the theory of so-called lane-related influence lines, allowing to determine most unfavorable effects. Unit loads are placed along the respective lane, and the corresponding influence on the individual internal force is determined. This approach does not only give the most unfavorable effects due to traffic, but also allows fast recalculation. In the next step, the most unfavorable influence is determined by integrating the load intensity along the lane. Actually, along the sections with unfavorable influence in case of distributed load. In case of individual vehicles with point load, the influence are multiplied by the vehicle load or X load respectively. In this step, also the resulting effects of individual lanes are combined between each other and in accordance with the respective code. This what I was actually explaining in the last 3 slides. We see now in this video, we see how easy it is interactively to 3D to define the traffic load. So to define the lane sets interactively on the building, which at the first point, the generic approach is demonstrated, which is code independent and can be applied to any code. And in the second step, we will see how we can do it in accordance with the standard, with the automatic definition, where we just define the building, the structure where we want to define it, and use this to create the lanes by standard by just selecting the width of the road, and the auto subdivision automatically is defined to the structure. So the next important implementation is the dynamic analysis, so the earthquake load evaluation, because a dynamic analysis is required for considering the effects of earthquake events, for example, the dynamic vibration behavior of the structure, and it must be investigated. This extension of the structural analysis feature is the most recent functionality, and the modal analysis method has turned out to be the appropriate method for determining the relevant structure response behavior of structures in earthquake situations. This method is recommended in most modern design codes, and in our case, it's already for Eurocode 8 seismic design already implemented. The effectivity of the method results from the fact that only few natural modes need to be considered, due to high frequency vibrations being almost completely damped out. So the first step in the calculation process is therefore the determination of relevant natural modes of the system, dependent on the structural stiffness and additionally on active masses, which must have been correctly provided in the BIM database. The amount of excitation of the individual modes in an earthquake event is governed by the frequency content of the occurring earthquake and by the damping properties of the structure, support elements, and any installed damping devices. Response spectra for common structures and typical earthquake events are given in the design codes and allow an easy evaluation of the relevant extreme response values. So in the solution uses the multi-mode response spectrum method for evaluating the effects of seismic loading. The solution consists of two separate tasks in the calculation procedure. So firstly, the determination of relevant natural modes of the structural system, and secondly, the evaluation of the response spectrum prescribed in the design code. So the natural modes of the structure are calculated on the undamped system by determining the roots of the homogeneous equation system. A subspace iteration scheme according to above is used to find the eigenvalues of this equation system, and thus the natural frequencies omega and relevant displacement directions for computing the mode shapes. The eigenmodes are normalized to a maximum displacement value of 1. They are saved to the database in order to allow for visualization and further evaluation tasks. In addition to the stiffness matrix, also the mass matrix is required as governing parameter for the eigenvalue calculation. It represents the oscillating masses of the structure. In the solution, the self-weight and the superimposed dead loads as defined for the static load case are automatically considered for calculating a consistent mass matrix. This ensures accurate results even with coarse element subdivisions. Any additional relevant masses can be easily defined by the user with their position and possible moment of inertia. In case of an earthquake, the actual extent of the different natural modes is dependent on the direction of the seismic waves, ground accelerations, for example, the corresponding mass participation on the damping behavior of the structure. The analytic solutions for typical structures and unique impacts are provided in the design codes as relevant response spectra, specifying the relevant proportionality factors for the individual eigenmodes dependent on the natural frequency. The calculated amplitudes related to the individual natural modes are superimposed using different methods described in literature. The solution offers the ABS method, SRSS method, DSC method, and CQC method. 3 separate calculations are provided to consider different possible earthquake directions, transverse, longitudinal, and vertical directions. These different cases are combined to get finally the envelope for extreme values. Also in this short video, how this definition works in the solution. So it's pretty easy to, according to standard, is defined. And as I've mentioned before, the tasks that need to be defined. So we need to calculate the eigenvalues of the structure. This is the first step. And then the earthquake response with the defined spectre is placed into the calculation model. And this allows us also, when we do some changes to the model, this definition will stay in the database and will be applied to any new geometry and to any new changes of the structure. So what is this integral software approach? So we know that a variety of design and proof checking procedures are required once the structure analysis has been performed and the relevant design forces have been calculated. They are based on national standards to guarantee safety and serviceability. Code-based design in the solution involves the use of an ecosystem of advanced technologies to cover all range of structural types used in practice. The first standard that is currently comprehensively processed is the Eurocode Standard 2 for concrete bridges. This procedure includes design tasks like the layout of pre-stressing tendons or reinforcement, and ULS and SLS checks for the cross sections. An easy and generally applicable design code engine provides most of the relevant procedures, starting with the stress check to keep linear stresses within certain limits. Even second-order effects of slender piers are considered, using the method based on nominal curvature due to imperfections and the effects of creep. One of the most relevant checking procedures in the ULS check of arbitrarily shaped pre-stressed cross-section for flexure with or without actual force, for shear and torsion, and considering the interaction of normal force and biaxial bending through an interaction surface. This solution is also connected to a general reinforcement detailing system, which allows to take over required reinforcement values from the design procedure and to add structural reinforcement not related to strength, but to construction works. This system can also be used for creating detailed reinforcement drafts and bills of materials. How to slowly come to our conclusion is that where we still see some of the problems here. So sometimes the work overload prohibits implementation of innovative tools in bridge companies and they start to use it. So how to practically implement the BIM in bridge industry? Management level in the company needs to stay behind the goal, implementation of BIM process, and choice of right tools for bridges. The processes need to be defined and followed, and nothing can succeed if the needs for such processes indeed are wished in the teams as well in the management level. And of course, this offers us a return of investment. So the BIM application in bridge engineering is becoming more and more popular. However, a holistic application is still seldomly executed. However, an integrated BIM approach can strongly raise the efficiency of the planning and construction processes. A new software solution addressing the relevant tasks to be executed in bridge engineering was presented here. So this approach aims to improve the planning process in terms of time as well as in terms of quality. Using the same model also for tasks arising during lifetime, for example, maintenance, inspection, and repair measures. This would further increase the efficiency. However, this extent is still in its infancy and would require general acceptation of the technology and better standardization of used software tools. So I'd like to thank you for your attention.
Thank you, Mr. Can Osterz. Do you have any question for this informative presentation? Raise hand, I see a lot to talk. Mr. Murat Akıncı, I see you raise your hand and I give allow to talk right now to you. Are you going to ask a question? Mr. Akıncı, can you hear me? Okay, I think there's some mistake.
Okay.
There's no question. Thank you, Mr. Can Osterz, again.
Thank you. Thank you.
Now, next presenter is Mr. Abdullah Al-Sarfin.
Hi, can you hear me?
Yes, we can hear you and see your presentation right now.
Okay. So yeah, I'm ready to start.
Okay, go ahead.
Okay. Hi everyone. I'm Abdullah Al-Sarfin. I'm actually filling in for Ali Banaipur, who couldn't make it today. Today I'm going to talk about qualifying commercial rapid repair media for partial bridge deck repairs in Utah. So this is a Utah Department of Transportation funded project. For this project, we investigated 8 different rapid repair material from 5 different manufacturers for their performance, for their mechanical performance, and then prepared a report. So let's dive into some of the backgrounds. So rapid hardening prepackaged repair mortars or concretes are being very popular recently because if you use these materials to repair the structure can be reopened to traffic in as few as 2 to 4 hours. So primary categories of rapid setting cement-based materials are magnesium phosphate cement, calcium sulfoaluminate cement, calcium aluminate cement, and other blended cements. So these mixes are these materials are easy to mix and are more compatible with the substrate, but they can be costly and more susceptible to shrinkage. Some of the causes of premature failures are exposure to freeze and thaw cycles, which is very important for an environment like Utah, where the temperature can vary between extreme ranges. Aggressive chemical exposure, mechanical abrasion, loss of bond between the repair and the substrate, and dimensional stability of the repair material. So for this project, we performed robust laboratory study for the mechanical performance and durability. The laboratory test included setting time, compressive and splitting tensile strength, static modulus of elasticity, autogenous and drying shrinkage, surface resistivity, and slant shear bond strength test. These tests were performed at ages of 4 hours, 24 hours, 7 days, and 28 days. This is a summary of the materials that we used. For our mixing, we strictly followed the manufacturer recommendation. By that mean that we strictly followed the amount of prescribed water, our mixing duration. So these 8 materials designated as from M1 to M8. Some of these materials contained fibers. I think, yeah, 3 of these materials contained fibers, and 4 of these contained pre-extended aggregates. So so for the initial and final set time, we followed ASTM C403 using a 150 by 150 millimeter cylinders by acme penetration resistance method. For compressive strength, static modulus of elasticity, and splitting tensile strength, we followed ASTM C39, C496, and so C469 respectively. And we used 100 by 200 millimeter cylinders with 3 replicates per test at ages of 4 and 24 hours and 7 and 28 days. Bond strength was measured by slant shear, and we followed ASTM C882 and C928 and performed this test at 4 hours, 24 hours, and 28 days. Surface electrical resistivity for every cylinders were measured prior to the mechanical testing. The standard that we followed was a ASTO TP95. Sorry. So autogenous shrinkage was measured with corrugated tube method, beginning at the final set. Rapid setting time precluded sieving of the materials that included coarse aggregates and fibers. So we were able to measure only 3 of these materials, M4, 6, and M7. For drying shrinkage test, we prepared a 3 by 3 by 16 inch or 75 by 75 by 400 millimeter concrete prisms, which were demolded at 4 hours and 24 hours, and followed ASTM C157 and C928 standards. Let's talk about some of the findings from our laboratory testing. So, so when we looked into the initial and final setting time, we found that the initial setting time for all of the materials were between 20 to 35 minutes, except for M2 and M7, which is actually more than an hour. M4 and M2 had the lowest and the highest working time, respectively. M2 and M7 are the only materials with a final setting time of more than 1 hour. Actually, for M2, it is almost close to 2 hours, and for all other materials, the final setting time was measured between 30 to 50 minutes. The time between the initial and final setting time for 6 out of the 8 materials were around 5 to 15 minutes. Most of these materials started to gain strength rapidly and come within actually less than 45 minutes. So, so for compressive strength, we used SHRP proposed classification system to categorize these materials based on their rate of strength development. So the first category is very early strength materials, which develops around 20.7 megapascal compressive strength in 4 hours. The high early strength or HES materials achieve at least 5,000 psi or 34.5 megapascal in 24 hours, and very high strength materials achieve compressive strength of over 69 megapascal in 28 days. So all of those 8 materials that we tested satisfied the requirement for VES materials with minimum and maximum 4 hours strength being about 20.7 megapascal and 38.6 megapascal respectively. For all materials except for M3 can be classified into high early strength material because their 24-hour strength was more than 34.5 megapascal. But the only materials that can be classified as very high strength or VHS material are M1 and M2. So very early strength materials quickly develop enough strength and a good choice for a small repair area, while the HES allows for pavement to be reopened to traffic in 24 hours. But when there is a substrate with very high compressive strength, very high strength material is preferred. So this plot shows the rate of development of compressive strength, these rates are very different for each materials. M1, 2, and M3 develop not only noticeable compressive strength at early ages, but also significantly and continuously gain strength after 24 hours. In these 3 materials, the late age compressive strength or 28 days compressive strength is nearly twice their 24-hour strength. This could be due to the hydration potential remaining in these materials after setting rapidly and quickly. On the other hand, for M7 and M8, we observed a low strength gain at early age and also insignificant strength development at late ages. But still, all these materials met the project compressive strength requirement. M4, 5, and M6 showed a considerable strength gain at early ages, but the rate of strength gain beyond 24 hours in these materials is not as high as M1, M2, and M3. So one of the important indicator for the performance of these repair materials is static modulus of elasticity. So the requirement is that the structural compatibility of repair material is having an elastic modulus close to that of the substrate concrete. Considering the elastic modulus of an H concrete deck being more than 27.6 gigapascal and elastic modulus between 27.6 gigapascal to 34.5 gigapascal can be considered as the desired range. So the elastic modulus for the selected rapid repair materials at the time of exposure to traffic, which is around 4 hours, is between 22.8 gigapascal and 32.4 gigapascal. And we observe different, just like compressive strength, we observe different rates of elastic modulus development. M5 and M8 did not show a very noticeable stiffness development at neither early nor late ages. However, these two materials are the only materials that fall in the desired elastic modulus range of 27.6 gigapascal to 34.5 gigapascal. So then we perform a split tensile strength test for normal weight concrete, nominal 28 days with a nominal 28 days compressive strength of 34.5 megapascal, and tensile strength of is around 2.76 to 3.45 megapascal. So therefore, the repair material should have a tensile strength of at least 2.76 megapascal to be considered acceptable. So four of the materials, M1, 2, 4, and 5, satisfy the tensile strength requirement at the critical age of 4 hours. At 28 days, all materials except M6 had a tensile strength higher than 2.76 megapascal. We observed different trend in tensile strength development. But just like compressive strength development rate, M1 and M2 had the highest tensile strength development. M4, M5, and M8 did not continuously develop tensile strength and showed a decrease in tensile strength from 24 hours to 7 days. And this behavior is actually more pronounced for M5 and M8. Both of these actually contains fiber. We measured surface electrical resistivity as a measure of concrete chloride penetrability. So these materials, so 3 of these materials, M1, M2, and M3 had a moderate, and M6 had a low chloride penetration potential at the critical age of 4 hours. All other materials had very low chloride penetrability at the age of 4 hours. So after this 4 hour period, all material developed surface resistivity over time, and their chloride penetration potential at 28 days were very low. The development of M1 was exceptional as its surface resistivity significantly increased beyond 24 hours, making its chloride penetrability at 28 days negligible. So to investigate the quality and strength of the bond between the substrate and substrate concrete and repair material, we performed slant shear bond strength because practically there is a state of shear at the repair substrate interface. According to STM-C 928, the required bond strength of for rapid set prepackaged repair material is around 6.9 megapascal. Is between 6.9 megapascal and after the first day, and is above 10.34 megapascal at 7 days. The lowest and highest bond strength at the critical age of 4 hours was observed in M3 and M4 respectively. At 28 days, all materials had a bond strength over 20.7 megapascal except M8. So M3, which had the lowest bond strength at 4 hours, had the most significant bond strength development among all materials. M2 and M7 had the highest bond strength development from 4 to 24 hours, but M2 did not develop much bond strength beyond 24 hours. M1, M5, M6, and M7 showed almost the same rate of bond strength development beyond 24 hours. And M8 followed an increase and then decreased trend similar to its splitting tensile strength development behavior. It also had the lowest 1 and 28 days slant shear bond strength. So this 4th figure shows the different failure mode that we observed during slant shear bond strength test. We found all possible failure patterns. These includes bond failure, repair material failure, substrate concrete failure, and a combination of all the previous 3 failure modes that I mentioned. In 4 out of the 8 repair materials, M1, M2, M3, and M6, bond failure was observed in 1 specimen only. M4, 5, and M7 experienced bond failure at early ages, but not at late ages. M8 is the only material having a bond failure at both early and late ages. M5 and M8 had the highest number of bond failures, and M2 is the only material having only repair or substrate failure modes. Then we performed autogenous shrinkage test on only 3 of the materials, M4, M6, and M7, because the 5 materials that we couldn't test for autogenous shrinkage had either fiber or pre-extended aggregates, or in some cases both. So what we found was that a significant portion of the total autogenous deformation of these 3 materials occurred in the first 2 to 3 days. M4 had the highest autogenous deformation at all ages, with about -50 and -60 microstrain at 24 hours and 28 days respectively. The deformation of -60 microstrain is still negligible, calling for further investigation through drying shrinkage test. M6 and M7 initially and at very early ages showed expansion, but it started to shrink afterwards. So there are 2 possible reasons for this phenomena. So the heat of hydration, which causes thermal expansion, and then the accompanying use of shrinkage compensating admixture, which causes the expansion to offset the material shrinkage. M7 had a higher initial and final setting time, so the material with more working time developed lower autogenous deformation. So then we check the volume stability requirements. The long-term shrinkage of the repair material should be equal to or greater than that of the substrate. So ASTM C928 requires that all allowable decrease in length change after 28 days to be -0.15% or negative 1500 microstrain for air-cooled test specimens. Crack development due to repair material shrinkage can reduce durability and cause premature failure of the repair system. The selected repair materials show different rates of drying shrinkage development, which reflects the fact that they are composed of a variety of cementitious constituents and admixtures. A substantial portion of the drying shrinkage occurred in the first few days, similar to what we observed in the autogenous shrinkage. Even for M6 to M8, with the highest drying shrinkage, these materials were able to satisfy the ASTM C928 requirements with a 28 days length change of about half the specified limit. So M3 showed the best length change performance, as it developed the lowest drying shrinkage at almost all ages. M7 and M8 displayed the highest length change due to free drying shrinkage. Both also have had poor mechanical performance. M2 and M5 showed an overall very low drying shrinkage at all ages. They had a small drying shrinkage within first few hours, possibly due to temperature loss, followed by a slow and steady rate of shrinkage growth over time. M6 and M8 had a rapid and large increase in drying shrinkage within first few days, and followed by a continuous and gradual increase in length change over time. In conclusion, we found that all the materials we tested met the requirement of their compressive strength after 4 hours. The time between the initial and final set time for most materials are found to be between 5 to 15 minutes, and materials commonly started to gain strength in less than 45 minutes. We found that the chloride penetration potential of all the materials at late ages are very low. 7 of the materials had a slant shear bond strength over 11 megapascal at 4 hours, while one material, except one material, all the materials showed a bond strength of above 20.7 megapascal at 28 days. All possible failure modes were observed in the slant shear. Hello?
Hello.
Yeah, I think the connection dropped at some point.
Yes. Yeah. Please
Okay.
continue.
Okay. At 28 days, 5 materials had a free dry shrinkage of between
But
200
we
and
cannot
400.
see your screen. Sorry.
You cannot see my screen?
Yes.
Okay. Let me check.
I mean, we cannot see your PowerPoint presentation. We can see
Okay.
it right now.
What about now?
Perfect. Thank you.
Okay. Thanks. Sorry for the trouble. So all materials generally had a satisfactory performance, but with different trends of autogenous or drying shrinkage development. At 28 days, five of the 8 materials had a free dry shrinkage between 200 and 400 microstream, while for other 3 materials, it was between 600 and 800 microstream, well below the ASTM specified SE 928 specified limit. Overall, based on the initial lab performance observation provided in this presentation, M1 and M8 showed the best and worst performance in terms of both mechanical and durability properties, respectively. Thank you for your time. If you have any question. If you have any question, I would be happy to answer. I think there is no question.
I'm sorry, there is some connectivity issues right now. So is there any question for Mr. Abdullah's presentation? I think there is no question. Thank you, Mr. Abdullah, for informative presentation. Thank you.
Thank you.
Right now we have a break, commercial break until 6 p.m. After 6 p.m. we will continue our keynotes, Mr. Khalid Mahmoud and Hani El Nagar. Thank you. You are invited to Istanbul Bridge Conference.
You are invited to Istanbul Bridge Conference.
Hello, greetings from Sheraton Istanbul Hotel Ataköy. You're invited to Bridge Conference in Istanbul.
İstanbul Köprü Konferansı'na davetlisiniz. Merhaba arkadaşlar, İstanbul Köprü Konferansı'na hepiniz davetlisiniz. İstanbul Köprü Konferansı'na davetlisiniz.
You are invited to Istanbul Bridge Conference.
Köprü Konferansı'na siz değerli insanlar davetlisiniz.
Good night. You are invited to Istanbul Bridge Conference.
You are invited to Istanbul Bridge Conference.
Hello, greetings from Sheraton Istanbul Hotel Ataköy. You are invited to Bridge Conference in Istanbul.
İstanbul Köprü Konferansı'na davetlisiniz. Merhaba arkadaşlar, İstanbul Köprü Konferansı'na hepiniz davetlisiniz.
İstanbul Köprü Konferansı'na davetlisiniz.
You are invited to Istanbul Bridge Conference.
Köprü konferansına siz değerli insanlar davetlisiniz.